Hello friends, I am Prashant V, Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to explain about the introduction to stiffness matrix method. The learning outcome of today's lecture. At the end of this session, students will be able to find out the degree of kinematic indeterminacy and they will be able to understand the procedure for stiffness matrix method of analysis. So basically a structure is designed for the stress resultants of bending moment, shear force, deflection, torsional stresses and axial stresses. The evaluation of these stresses, moments and forces and plotting them for that structural component is known as analysis. Whereas the determination of dimensions for these stress components and proportioning is known as design. Structure is generally classified into two categories, that is determinant structure and indeterminate or redundant structures. So determinant structures are analyzed just by use of basic equilibrium equations. So these basic equilibrium equations are summation of f of x is equals to 0, summation of f of y is equals to 0 and summation of m is equals to 0. By this analysis, the unknown reactions are found for further determination of stresses. Whereas in redundant or indeterminate structures, these structures are not capable of being analyzed by mere use of basic equilibrium equations. These structures along with basic equilibrium equations need some extra conditions that to be used for determination of unknowns. So the conditions may be compatibility conditions of deformations. Then we can find out the unknowns. The analysis of indeterminate structure is the major field in structural analysis. There are several methods of analysis. The need for the analysis of high degree indeterminate structure and development of computers have given rise to a new method called matrix method. So broadly, the matrix method of analysis are categorized in two ways: flexibility matrix method and stiffness matrix method. Flexibility matrix method, this method is also known as force method or static method or compatibility method. Whereas stiffness matrix method is also known as displacement method or kinematic method or equilibrium method. The points to be considered during the stiffness matrix method: here primary unknowns are joint displacement. This method deals with kinematic indeterminacy of the structure. In this method, primary unknowns are vertical displacement, horizontal displacement and rotation at joints. Primary unknowns are found out by solving the structure equations of equilibrium. This method uses slope deflection equations. By knowing the displacement and rotation to meet the serviceability criteria and checking rotation capacity makes this stiffness matrix method more practical. This method is more preferred for the analysis of large and highly redundant structures. This method is easy to program in computer softwares and hence it is widely used in professional practice. So stiffness matrix method is known as, so here pause the video and try to write answer on a paper. This method is also known as displacement method or kinematic method or equilibrium method. Now we should know what is degree of static indeterminacy and kinematic indeterminacy. The number of equations required over and above the equation of static equilibrium for the analysis of the structure is known as degree of static indeterminacy or degree of redundancy of the structure. A structure is said to be kinematically indeterminate if the displacement components of its joints cannot be determined by compatibility equations alone. For this structure, additional equations based on equilibrium condition must be formulated. The number of equilibrium conditions needed to find the displacement component of all joints of a structure are known as degree of kinematic indeterminacy or degree of freedom. So here we will understand what will be the degree of freedom at the end. So for free end, so here you can observe the end B. So at end B it is free. So here the degree of freedom are free. So as the joint B is able to move in horizontal direction, vertical direction, and also it can rotate. So in the second next figure, here you have a roller support or simple support. So here the moment is not allowed to move in vertical directions. So the joint B can only move in horizontal direction and it can rotate. So here the degree of freedom is 2. In the third figure, you are having a hinge support. So hinge support will not allow to move that joint in vertical direction nor in horizontal direction. Only the rotation is allowed. Hence the degree of freedom here is 1. You see the whole beam end is fixed, other end is also fixed. So what will be the degree of kinematic indeterminacy? So here the joint A and joint B are not allowing to move in either horizontal direction nor vertical direction, nor they are allowing rotation. Hence the kinematic indeterminacy is 0. So in propped cantilever, one end is fixed, other end is having a simple support or roller support. So here the degree of kinematic indeterminacy is, that is the degree of freedom. So here there is 0 degree of freedom, and here the degree of freedom, here it is 2. One is horizontal movement and other is rotation. Now in this figure, last figure, one end is hinged, other end is roller. At A joint, it is a hinge support, so it will be having only 1 degree of freedom, that is rotation. And joint B is a roller support, it is having 2 degrees of freedom, that is horizontal movement and rotation. Therefore here the degree of kinematic indeterminacy is 3. Now we will see the kinematic indeterminacy for pin jointed truss or frames. For plain frames it is 2j minus E, and for space frames it is 3j minus E. So here you can see a pin jointed truss, that is plain frame. So here the degree of kinematic indeterminacy will be 2j minus E, where j is the number of joints and E is the number of unknown reactions. So here you can see the number of joints 1, 2, 3, 4, 5 and 6. Then the unknown reactions are, so here at the hinge, vertical reaction and horizontal reaction 2, and for roller only 1 vertical reaction. So therefore 2j minus E, that is 2 into 6 minus 3 is equals to 9. Therefore for rigid jointed frames, in plane frame it is 3j minus E, and for space frame it is 6j minus E. So you can see the number of joints here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So J is 12. And the number of unknown reactions, so 3 unknown reactions for each fixed support, that is 9 unknown reactions are there. So decay will be 3j minus E, that is 3 into 12 minus 9 is equals to 27. Now we'll see the step-by-step procedure of stiffness matrix method. Step 1 is to determine the degree of kinematic indeterminacy, that is the degree of freedom. Then we have to assign the coordinate numbers to the unknown displacement. The basic unknowns are delta 1, delta 2 up to delta n. The displacement in coordinate direction 1, 2, 3 up to n. So impose restraints in all coordinate directions to get fully restrained structure. In other words, we have to start the analysis with a restraint structure. Step number 4, determine the forces developed in each of the coordinate direction of a fully restrained structure. It is called PL. Forces developed due to the applied load in the restraint structure in the coordinate direction B, P1, P2 up to Pn. Step 5, determine the stiffness matrix K and displacement delta by giving unit displacement to the restraint structure in each coordinate direction and find the forces developed in all other coordinate direction. Here we have to give a displacement, unit displacement in one direction, and due to the displacement what will be the forces developed in other coordinate directions are to be determined. Observing the final forces in various coordinate direction, note the final forces as P. Now solve the stiffness equation, that is K matrix into delta matrix is equals to P minus PL matrix to get the displacement in coordinate direction. So this will have the equation P matrix is equals to PL matrix plus K matrix into delta matrix. So K into delta matrix is equals to P matrix minus PL matrix. So that will be is equals to P minus PL matrix. So solving this stiffness equation, the displacement in all the coordinate direction can be found. So these are the references which I have referred. Thank you very much for watching my video.